All right, next up we have Ozan speaking about optimal commissions and subscriptions in networked markets. You should say your last name. I didn't know how to pronounce it.
Candogan. Thank you for the introduction. It truly is a pleasure to be here today and tell you about my recent work with John Birge, Hongfan, Chen, and Daniela Saban. This work is motivated by the prevalence of markets that facilitate the exchange of goods and services between individuals. You can go ahead and purchase goods from others on eBay, find accommodation on Airbnb, or find freelancers to take care of some tasks for you on Upwork. In these platforms, the platform does not dictate the transaction prices, but rather these prices are formed endogenously. And the other thing that I find interesting is that not all buyers and sellers are compatible. So some buyers can trade with a subset of the sellers, but not the rest of the sellers. Thinking about Upwork, you will have some freelancers who post high, others who post low prices, and some freelancers have skills that make them compatible with certain tasks, but not the others. The platforms match the buyers to sellers in these markets, and they also charge the participants of the market some commissions or subscription fees. When I say commissions, I'm really thinking about variable fees. So if the buyers and sellers transact at a price of $100, Airbnb would charge 3% of that price to the hosts, to the sellers, and something between 0 to 20%, something variable, something type dependent to the agents on the other side of the market. When I say subscriptions, I'm really thinking about fixed fees that does not depend on the transaction price. You can charge them in a monthly basis, but some platforms just charge it in a per transaction basis. Amazon charging $1 to each third-party agent that's transacting on the platform would be an example of this. At the end of the day, the revenues of the platform depend on the chosen commissions and subscriptions, the price at which the buyers and sellers transact, as well as the number of transactions that take place. In this work, what we would like to explore is how the platform should the commissions and the subscriptions with the objective of maximizing their revenues. If there is an underlying network where not all types are compatible with each other, you may want to think about the network structure as you're optimizing over the commissions and subscriptions, and we would like to understand the role that the network structure plays as we determine the optimal commissions and subscriptions. In practice, simple commission and subscription schemes appear as well, and we'll try to understand limitations and scope of simpler commission and subscription schemes once we characterize the optimal ones, and we'll try to bound the profit loss due to using simpler schemes. And time permitting, I'll tell you about some new results that we have on the welfare front. If you focus too much on revenue maximization, are we going to mess up the efficiency in the market? Can we bound the efficiency loss, and so on and so forth, is what I would like to come to at the end. Let me dive right into the model. I'm going to think about a market where I have finitely many buyer types, finitely many seller types. Each type has an associated mass of infinitesimal agents. I'm going to denote the population of type I sellers with SI, type J buyers with BJ. And I will have a very simple preference model. In particular, I'm going to associate a value distribution with each seller type and with each buyer type. And I'll have a bipartite network that captures the compatibility between different buyer and seller types. So coming back to here, on the right-hand side, I have my buyers. On the left-hand side, I have my sellers. Type 1 buyers are compatible with type 1 sellers, but not with type 2 sellers. The primitives of my model, therefore, are the populations, SI, BJ, the value distributions, and the underlying network. And one simplifying assumption that I'm going to impose throughout is the stuff that I have at the bottom of the slide. Each seller has one unit of good or service to offer. Each buyer demands at most one unit from a compatible seller. So a buyer of type 2 over here has the same value for the good if she trades with a compatible type 1 or type 2 seller. Okay, that's going to be a simplifying assumption that I'm going to impose. Now, filling in some of the details, I talked about commissions and subscriptions in the beginning of the talk. Here's how I'm going to model them. The platform chooses a vector of commissions which possibly assigns a different commission rate to each seller type. And similarly, I can associate different commission rates with different buyer types on the other side of the market. And similarly with the subscription fees, the thing that I would like to emphasize here is that for now, these are type dependent. I may want to offer a different commission to a type depending on her position in the underlying network. It's instructive to see through an example what agents' surpluses look like if they trade at a certain price. So let's look at this example. Suppose that a type I seller is transacting with a type J buyer at price P. In the context of our model, the buyer is going to pay, let's see if I have, yeah. The buyer is going to pay P dollars. The seller is not going to receive the SOL because the platform is taking a cut. For transacting on the platform, the seller may be charged an additional fee. So that's paid away as well. And since I am giving away the item that I have, I may have a disutility associated with that. So this is my surplus if I am a type I seller transacting at this price. And similarly, for the type J buyer, I can actually write down what the surplus looks like. The point is, if you know at which price the buyers and sellers are transacting, you can easily write down what their surpluses look like. The thing that I would like to capture, though, is the fact that prices are actually formed endogenously. And to formalize that, I'm going to look at a competitive equilibrium model. And I guess going back to the previous talk, in this model, there is no Bill Gates. Everyone is Scott. So everyone has the same value for money. And we are going to keep that assumption throughout. So let me try to go ahead and define what I mean by a competitive equilibrium here. Fix the commission vector and the subscription vector for a second. Competitive equilibrium will be a tuple of prices and trade decisions such that these two conditions hold. What do I have here? Well, fix the price. This P vector is a price vector that associates a price with each seller type. Think about seller type I. If I am offering my good at a price of PI dollars, I may end up paying a commission and perhaps some fixed fee on top of that. And the net transfer to the type I seller trading at price PI is this quantity. Any seller who has lower price will trade the total number of buyers, total number of sellers of type I who are willing to trade at this price is just given by this quantity QSI. I have my induced supply. I have my induced demand. And if the prices are such that, given the induced supply and demand, I can match the buyers to sellers who are willing to trade at these prices and clear the market, that tuple is my competitive equilibrium. All right? Now, OK, so far so good. What I would like to do is to go ahead.
On the previous slide,
yeah.
On the second for demand, why is it IJ and not JI for XIJ?
In the second one?
Number 2, the second bullet.
Here?
On the rightmost. Why is it IJ? On the rightmost, like XIJ. Why is it IJ not JI for demand?
We follow the convention that XIJ is indexed by seller first and buyer next.
And then on the previous one, it's like, why is it IJ for both? Shouldn't it like alternate for supply or demand?
I'm summing over all edges, fixing the I coordinates here. I'm summing over all edges, fixing the J coordinates here. Yeah. Now back to here. What do the platform's revenues look like? Let me formalize that, and then we are going to go to the results. Suppose that I fix my commissions and subscriptions, and some mess of buyers, QBJ, are trading on the market. If a buyer of a certain value is trading, any buyer who has higher value would be willing to trade as well. I can go ahead and figure out who the marginal agent is. So I can actually figure out the value of the agent, of the buyer, who is still trading, but who has the lowest value among all trading buyers. Given that she is the marginal agent, her surplus is 0. She's indifferent between trading or not trading, which means that the total transfer from this buyer to the rest of the system is exactly her value. All buyers of the same type, when they trade, make the same transfer to the rest of the system. This transfer includes the price I pay, the commissions I pay, the subscription I pay. But the net transfer for any trading agent, any trading buyer, is given with this quantity. Multiply it with the population of the buyers who are trading and sum it over all the buyers. This is the total transfer from the buyers who are trading to the rest of the system. minus the transfers from the platform to the trading sellers. So amount the buyers pay minus the amount the sellers receive is the revenue of the platform. The optimization problem that I would like to solve is this one. I would like to choose my commissions and subscriptions such that at the induced equilibrium, the revenue of the platform is maximized. I make some regularity assumptions on the distributions. The objective is nice and concave, but the set of constraints I have is nasty. It is going to be non-convex in general. And this is coming from the fact that I have these two sets of constraints. And the first set is actually nonlinear and maybe not as easy to deal with. I'm going to do the obvious thing. I'm going to relax the nonlinear constraints, and I'm just going to impose the second set of my equilibrium constraints. So now, if you look at the problem that I have, this is a mean cost network flow problem with convex edge costs. It's a nice convex optimization problem. Qualitatively, what I'm saying here is that as opposed to optimizing over commissions and subscriptions, I am going to pretend that I can choose the population of buyers and sellers who should trade at the equilibrium, with the hope that at the end of the day, I will be able to back out the commissions and subscriptions that support these trading masses at an equilibrium. It turns out that this relaxation is tight. That is, you can solve this problem, identify the masses. I mentioned that it's a network flow problem. You can go ahead and look at the supporting node potentials, from which you can reverse engineer the commissions and subscriptions that actually achieve the optimal profits at the solution of this problem. So I can actually determine what the optimal commissions and subscriptions look like by solving this convex problem. Side remark here. Here, basically, we are optimizing over the marginal agents. This idea is not new in that, in other settings, you can actually think about optimizing over marginal agents for a platform who's trying to maximize revenues or other objectives. One caveat here is that we need to be careful about the flow constraints that we had to impose for market clearance, but it turns out that you can take care of that. Now, the other thing is that you can always reverse engineer the commissions and subscriptions that support the optimal revenues, but in general, they won't be unique. For an obvious reason, you might be able to maximize your revenues by just charging commissions or just charging subscriptions, right? Fixed fees or variable fees, they will both be sufficient for maximizing revenues. The other thing, which is perhaps a little bit more nuanced, is the following. For profit maximization or for revenue maximization, in general, A, I will need to charge agents on both sides of the market, and B, I may need to discriminate different types according to their network positions. Let's talk about the impact of the network structure a little bit, and I'm going to come back to this idea of charging different sides, different fees, and discriminating agents. I will try to address what happens if you were to restrict attention to simpler schemes later on. So in the paper, we have a characterization of the surplus of types according to their network position. In the interest of time, I'm not going to talk about this one, but what I'm going to talk about is the network structures that actually yield higher revenues for the platform under the optimal commissions and subscriptions. To that end, I'll introduce this concept over here. This is a weighted version of the Hall's marriage theorem, Hall's marriage condition. If I didn't have the ratio over here, that would be the Hall's marriage condition, which says that the network is such that I can assign each buyer to a unique seller on the other side of the market. I have the scaling on the right-hand side. I'm multiplying the right-hand side with the ratio of the total mass of sellers to buyers in the market. And this is basically saying the following. If it is not the case that I have a set of buyers who have very few sellers on the other side of the market, if supply is somewhat balanced across the network, then the condition is going to be satisfied. So you can think about it as a condition for understanding when the supply is more or less evenly distributed across the network. And I have an approximate version of this one as well. Why do I care about that? Why did I introduce this to you guys? If it is the case that both agents on the both sides have identical value distributions in the simplified setting, then actually among all network structures with the same population of buyers and sellers, the ones that satisfy the weighted Hall condition are going to maximize the revenues of the platform, And if if this condition holds approximately, you can also guarantee approximate revenue maximization. We have a similar characterization for surplus of the buyers as well, but I'm not going to talk about that in this talk. The takeaway from this result is that more balanced structures in the weighted whole sense, more balanced structures under optimal commissions and subscriptions yield higher revenues. Now, before I wrap up, let me comment on this last point here. If you look at what platforms are doing in practice, you see that some platforms are just charging agents on one side of the market. Other platforms end up charging both sides, and on one side they're offering homogeneous commissions. On the other side, Airbnb offers discriminatory commissions. So, okay, these are still simpler than the optimal commissions and subscriptions that we have identified. So how do simpler schemes perform? How does it in particular perform to charge identical payments to all agents on one side? And how does it perform to focus only one side of the market? In general, if you rely on homogeneous commissions, the revenue loss can be arbitrarily bad. However, if it is the case that distributions are well behaved, you can get 1/2 of the optimal revenues by using homogeneous commissions. Or if the supply is balanced across the network, again, the revenue loss is going to be small. To complement this, with this question of what happens if I charge payments to agents only on one side of the market, I have this other result, which says that if you are charging payments only to sellers or only to buyers, in general, regardless of the distribution, you can guarantee 1/2 optimality. So perhaps, qualitatively, simpler schemes that allow for discrimination on one side but not both sides are not too bad. And if it is the case that one side of the market actually has homogeneous distributions, I think I have another minute. If one side of the market has homogeneous distributions, then it actually suffices to charge payments to agents only on the other side of the market. So one-sided extraction is not bad in a rich set of settings. And let me have this as my last slide. A natural question is, okay, you are focusing on revenue maximization, but what happens to welfare if you actually work with the revenue maximizing commissions and subscriptions that target certain types according to their network positions? If the distributions are arbitrary, then welfare loss can be substantial. But otherwise, if the value distributions are uniform or they are homogeneous within sides, then it turns out that the welfare loss is not too much. It is three quarters in one setting, 2/3 in the other setting. These numbers may look familiar from the price of anarchy literature. We are still trying to explain formally why that might be the case. I don't have an answer for that yet. So that is it. The paper is really about choosing commissions and subscriptions optimally for revenue maximization purposes in network markets. We try to understand how to exploit the network structure and when exploiting the network structure is actually worthwhile. Thank you for your attention.